So we've previously talked about reliability in theory. We're comparing what we observe for test scores to the true test score. Unfortunately, as noted in the lecture notes, we can't always measure the true, that we don't know the true. So since we don't know the true score, we really don't have a good handle on reliability, and that means we're going to have to look for other ways to measure reliability. In a sense, we're looking for a way to infer the true score. So if we don't know the true score, we could, well, there's a couple of other techniques that we could use. We can do multiple parallel tests. If we design a couple of tests and everything else is the same, then if the tests are truly measuring the same construct, the true scores on one are the true scores on the other, and those tests ought to have the same level of error variance. And we can use that to our benefit. So what we tend to do in classical test theory is look at correlations between parallel tests, and that is equal to reliability. That is the replication technique that I talked about. Mathematically, the correlation between the two tests, x and y, should be equal to the covariance between the x and y scores divided by the standard deviation of x times the standard deviation of y. And since those variances are the same, then what we really have is the covariance in xy divided by the standard deviation squared. And since the standard deviation squared is the variance, our correlation between x and y, the correlation coefficient, is going to be the true score squared divided by the observed score squared. So we're back to our proportion of the observed variance that relates to the true variance, and we estimate that by the correlation or the covariance between x and y. In domain sampling theory, instead of doing parallel tests, we have an infinite population of test questions, and we select test items from them. So basically, since we're selecting at random, the pairs should have the same mean and standard deviation, i.e. they be parallel. Sometimes this is also called generalizability theory. So here we did parallel tests. Here we did sampling of test items. And again, it's the same thing. We're trying to roughly estimate reliability when we don't know true test scores. So that leads to another type of reliability called alternate forms reliability. And again, we went over this in lecture notes. You can Google it. If differences in observed test scores correlate from one test to another, we can infer that the tests are reliable. This assumes parallel tests, and that's always a practical problem, whether you can actually do it. When you take tests multiple times, there are carryover effects, and so the errors in one can relate to the other. Alternate forms reliability assumes similar means and standard deviations. Again, very similar to parallel tests. You could have a test and a retest. You could have people take the same test to avoid the alternate forms problems. But again, participant scores may differ across time based on reasons and their carryover effects. That drives reliability testers to actually using a test within itself to measure reliability. And in doing this, we use different parts of the same test to function like a parallel test. So if a test's parts are highly correlated, then the test is likely to be more reliable. And this means that longer tests are more reliable than short ones. One of the major types of reliability measurement here are what's called split half estimates of reliability. We have a test, we split it in half. That gives us two parallel tests. So we get two subtest scores. we look at the correlation between the subtests and use that split half correlation to compute a reliability coefficient. Remember, we talked about the coefficient of reliability between the two halves. And we evaluate it using a Spearman-Brown formula. I'm going to illustrate this to you on an Excel spreadsheet. It's a difficult concept maybe to grasp. I don't care that you do the math at all. What's important is that you get the concepts that we're splitting a test in half and looking at the correlation between the halves. So here is a 10 people took an 8-item test. And the test scores are from 0 through 5. Actually, everybody got at least a 1 here. And here are their scores on those 8 items. So we have 8 questions. Those are our items. Here are the scores. And so we do our mean for each of the items for 3.7, 3.2, and so forth. We total the scores. Well, with these means, we now do a variance. And so we literally subtract the mean, that's B13, from the score. First one's B3, and we square it. So you see our formula up here, that's the difference squared. And that's our sum of squares. And the average variance, it divides it by 10. And so basically our variance is the average of the sum of squares divided by 10. And our variance for item 1 is 1.4. So we do that for each of the other items. I took these variances that we calculated, I copied them into these cells right here so that we have a mean and variance by item. Next step, we get a total score by person. We get a score for the odd questions. We get a score for the even questions. So we split our halves by odd and evens. And once again, we get a mean and a variance for the odds and a variance for the evens. And that's what we have in here. You could split your halves 1 and 2 and 7 and 8, 3, 4, 5, 6. And here are the total scores, and here are the variances for splitting your half, for splitting the test that way. So, second way of going about it. And a third way is we could do the first half and the second half and sum the scores and find their variances. And we've done that in these cells. Okay? So here we have those variances. Next, we find covariance. Covariance is the way one variance relates to the other. So here we have the score less the variance, less the mean, L13, so we have K3, which is the score, minus the mean, times, that's for odd, times the score minus the mean for the even. That's the covariance. That's how the odds and the evens relate to each other, those two halves. And so we get our covariances here for our first test. These are the covariances for the first split. Second split is number 2 here. Here are the covariances for that. And here are the covariances for the third split, the first half and the second half. The correlation coefficient is the I'm sorry, before I say that, to get the covariance overall, we average the covariances for each of the people. So here's our overall covariance for split half 1, average covariance for split half 2, average covariance for split half 3. We take those average covariances, that's what's in R13, S and T13, we divide that by the standard deviation square, standard deviation of one times the standard deviation of the other, and that gives us our correlation coefficient for this half and this half and this half. Now, what probably should jump out at you right away is that these are so different. Truthfully, if your questions were reliable, I mean, these shouldn't be this wildly disparate, but they are. Finally, we calculate the Spearman reliability formula, and that is 2 times the correlation coefficient divided by 1 plus the correlation coefficient. And we get 3 different measures, 0.61, 0.27, and 0.83. Basically, this suggests that there is a lack of reliability in these numbers because it's so low. You're going to want to have something over 0.5 probably to conclude that it's reliable on the split halves. And you know, it shouldn't matter how you split them, and this does matter, so that's a problem with interpreting these results. In any event, this is a simple example of split half estimates of reliability and developing some mathematical constructs to do that. The real question is, does it matter? You know, are these halves related to each other? And based on split half 1 and split half 3, this one pretty much looks like it. So anyhow, this is a way to get around not knowing the true scores. And in this methodology, we look at the relationship of test items one to another using split halves. Thanks.